So welcome back after coffee. So I'm Dalan Bailey from the Pirbright Institute, co-director, together with Erica Bickerton, who unfortunately couldn't make it today. So it should have been a double act, but hopefully you're okay with just me. So moving on to the countermeasures and interventions session. So I'm delighted to present Professor Saye Khoo from University of Liverpool, who's going to talk about clinical evaluation of experimental antivirals.
Thank you. Thanks very much. Thank you. Thanks. Can you hear me? Is the mic on? Yep. Okay. Thanks for the kind invitation. I'm an infectious diseases clinician, so somewhat of an intruder here, and I learned a lot from the posters last night, the excellent talks today, so thank you very much. I'm going to talk about clinical trials and the clinical evaluation of antivirals and the challenges in a pandemic. So here are my declarations. The Agile funding is from MRC, UKRI, Wellcome, and industry. And I'll touch on this, we also do much work around the pharmacology and the therapeutics, including drug interactions, and that's funded by industry. Okay, so straight on to the challenges. Conventional drug development, which I'm sure you'll know quite a lot about, is simply not designed for a pandemic. It's far too slow. It's not responsive to a population that has changing immunity, changing disease severity, where we're learning new ways of clinical management. So the effect of steroids, for example, the effect of use of CPAP and the judicial use of oxygen and supportive technologies has completely changed the mortality. So you've got a baseline that's changing throughout the pandemic, let alone the VOCs. And in the initial phase, there were lots of candidates put straight into large RCTs for completely understandable reasons, who would not have passed the threshold for evidence for inclusion during peacetime, okay? And you know what those are. The other issue is that there was much talk about repurposing, which is the first thing we do every time a new virus appears. And my view is that it's always a stopgap. If you look at the transformational changes in HIV, hepatitis C, that was not from repurposed medicines, okay? So it's not the destination. And MABs are fantastic, relatively quick, but not a globally scalable solution. And research is in a challenging environment. Hospitals are shut down, people with infection who we want to study are in home quarantine, etc. We initially had to rent porta cabins and drop them in supermarket car parks in order to start our studies going, because we just could not get them into hospitals. And there are opportunity costs. Bad trials cost lives, and you don't need a reminder of this. Even in the last month, we've had data from the active trials on ivermectin, but there will always be non-believers. So how do you transform conventional drug development to where we want to be, which is here, okay? And I don't expect everybody to be specialists in this, so I'll just quickly go through. There's all the preclinical stuff, which you'll be much more familiar with than I am. Then in phase 1, we do these SAD-MAD studies, single ascending dose, multiple ascending dose, usually about anything from 2 to 5 tiers, dosing tiers. And we go up, so we give single doses of escalating doses of drugs, and then we watch and we see how people respond to it and how safe it is. And then we give multiple ascending doses, etc. And each of those trials singly is treated statistically as a separate trial, okay? And that's what takes time. Then we go into phase 2, where we look for readouts, PK/PD, and all the other things, and then we go to phase 3. Now, phase 3 can only be shortened by so much. So to really compress and accelerate trial development, you have to condense the phase 1 and phase 2. And it seemed to us that 5 things needed to happen. You had to have a process where the promising candidates that would get through anyway, but they'd get through much faster. That you'd have to screen out the less promising candidates, and you accept the price of screening out candidates with more marginal effects in whom, in a population level, there would be aggregate benefit, okay? You want to accelerate decision-making. Too much time spent agonizing over whether to progress or not, what the right dose is, etc. And you want to compress the phase 1, phase 2. So there's a seamless transition between phase 1 and phase 2. So while you're evaluating the safety and optimal dosing, you're also looking at PD readouts, okay? And you want to be able to test multiple candidates at once, not in series, but in parallel. And that essentially is the concept that we went to for government funding. So Agile is a government-funded early phase platform for evaluating COVID treatments, but primarily focused on directly acting antivirals. And the ethos is that you have to meet, during the pandemic, you have to meet the drug at wherever state it's at. If it may be already be first in human, or it may be late preclinical, it may be at GMP tox, all those kind of, you have to meet the drug where it is. And when you pass it on, you have to pass it on to a platform which hasn't got any more gaps, so that it can say, right now we've got enough data on safety to go and evaluate population effectiveness. All right? And the way to do that is in a master protocol where you have an overarching protocol, and then each candidate is tested separately with contemporaneous controls. So you have sharing controls across the arms, but making sure they're contemporaneous, looking at drugs or combinations of drugs, starting at different times and dropping drugs off. And you can adapt the ratio of controls to endpoint. You can adapt the endpoints according to whether the drug is going to be given in hospital or in the community, and whether it's an antiviral or otherwise. Okay, so this is the, and I won't bore you with the protocol, but it's all in the public domain. So how does it work? So I'm going to give you an example with molnupiravir, which is a study that a drug that we've taken all the way through this platform. So we look at COVID-19 patients. There's a process of screen, consent, randomization, and then they're randomized into phase 1 into, in the case of molnupiravir, 4 dosing tiers. Okay, and it's important to say that in conventional drug development, each one of these would be a statistically separate standalone trial evaluated in larger numbers of patients that we had. So in each of these dosing tiers, we only had 6 patients randomized, 4 to active, 2 to control, okay, which is standard of care. You follow them through, so you do drive-by recruitment. You follow them through. The primary endpoint is treatment limiting toxicities at day 7, but you follow them right through day 28, or in the case of a monoclonal antibody, 9 months. But all the while you're evaluating these time points, and then you make the decision whether to expand that cohort or to progress or to stop. And at the end of that, you progress hopefully to phase 2 seamlessly again, and then you've got simple rules of futility and efficacy which allow you to drop or progress a candidate. There are certain things that are different from conventional trial development. So the first one is that the first in human trial can be in COVID patients. That's not usually the case. In fact, that never is the case with drug development. But there was no time to do, and no capacity to do healthy volunteer studies. And because your comparator have got COVID, you're going to have a very high level of toxicities and adverse events. In order to tease out whether it's a drug effect or disease effect, you have to randomize and blind, which is, again, unusual in early phase trials. You do a model-based assessment of toxicity, not summary statistics of frequency of adverse events, but probabilities of adverse events. And I'll show you how that works. And then the seamless progression between phase 1 and phase 2. There are very nimble committees that review safety together with the regulators and sponsors. And then we use a Bayesian platform which is statistically efficient, but it's used primarily for one reason only, and that's to accelerate decision making. So how this worked in phase 1 is that the Bayesian model, of course, requires a prior. And we set a prior, and I'll show you how we do that, in order to look at, in order to gain information and use information across different arms of the study. It borrows information across the arms. And so a dose-limiting toxicity, a dose is deemed unsafe if there's a greater than 25% chance that the treatment gives a 30% or higher rate of dose-limiting toxicity over controls, okay? Get your head around that. I'll show you how that works. And then the model also allows you to set the next dosing tier as that which is closest to 20% increase in DLT. So we accept a 20% excess risk of toxicity. That's a priori. And this model then allows you to skip dosing tiers if it's safe, right? Allows you to skip. There are rules about how much you can skip by, so you can't more than double the dose. So here's how it works. So at the start, you don't know. This is a new drug. You don't know what the toxicity is, so you guess, and that's your prior. So we guess that the risk of toxicity in controls would be 13% because they've all got COVID and they're going to have side effects. So we guess that that rate is 13%. We've guessed that the doses increase the rate of toxicity by a certain amount as the dose increases, right? And so that's the relationship between these doses increments. And then we're not sure about that, so we set a credibility interval, okay, an uncertainty, and that's worked out using a probability density plot. So this is all simultaneous. This is not dose one study, dose two, one study. This is all one study. Each of these points are informed by a distribution, a density distribution of a probability of toxicity changing as you go up. And then you study dose one. And then depending on what you find in dose one, you put these posterior probabilities in the model, and the whole model adjusts for dose 2, 3, and 4. Do you see how that works? Okay. So this is how it works. We started molnupiravir on 300 dose 1, 400, 600, and 800 milligrams twice a day because we knew from animal models that was where we wanted to go. We didn't want to go too high because we would run into concerns around genotoxicity. So that was the probability density model of the 600 milligram twice a day model before we started, okay? And then when we started on 300 milligrams, the 600 milligram model changed. And you can see that the risk of toxicity over 30% was 27%, so it was higher than the 25% before we started. But after we did the 300, the 600 milligram was allowable, and so that allowed us to skip the 400 milligram study just on 6 patients, 4 of whom got drug. Okay, we'll talk about limitations of this method later on. And so we progressed it through 3 cohorts, 18 patients, and you can see that 3 things happened here. First of all, the base assumption in the standard of care toxicity, which we set at 13%, actually became more like 3.5%, okay? Secondly, the incremental toxicity with incremental dosing was less than we had thought. And thirdly, the certainty, the confidence that we could say that was also much higher. So at the end of our optimized dose, which was 800 milligrams twice a day, that was actually had a toxicity level that we had presumed would be there at the first dose. Okay, so this allowed us to rapidly say that 800 milligrams twice a day was the optimized dose, and indeed Merck arrived at that conclusion some 6 months later and produced their own study. So then we moved on to phase 2. Of course, we then look at different things. So phase 2 is more conventional in a sense for clinical trials. But we looked at virological endpoints, and I need to say that the reason that we look at virological endpoints is because these early phase trials have not a chance of seeing any difference in hospitalizations or death, okay? And we're not using that to impute clinical efficacy, but we're using that to determine killing power. So we're saying you have an antiviral, you've got to kill the virus in order to be a credible candidate for progression. And there are futility and efficacy threshold based on hazard ratio of greater than or greater than 1. Okay, so this is the study. It's in Press in Lancet Infectious Diseases. 180 people. Quite a detailed study. So 1,700 people were screened to get the 180 people because it was many visits. It was safety, early phase trials. There was 8 nasopharyngeal swabs. I think if you've ever had one, that's one too many. So it's not a very pleasant study to be in. Bottom line, the drug was safe at across all the doses, but at 800 milligrams, which was the optimized dose in this study, phase 2. and that there was a signal of virological effect. So the time to PCR negativity, a flawed endpoint nowadays, I think, was 8 days versus 11 days. That most of that, if you cut a long story short, if you did 2 different tests, you got slightly different results on the limit of statistical significance. So the first one, the log rank, assumes proportional hazards, and the second one does not. So in other words, the antiviral effect happens very early on, so that in the first 7 days of treatment. So you wouldn't see that over 28 days. That's our non-proportional effect. So if you use the correct test, you would see a difference. The primary efficacy endpoint in phase 2 was deemed by us to be having a probability. So you want to look at the magnitude of effect and the probability of that magnitude. So you look at 2 things, okay? And to make that decision to accelerate the drug into phase 3. And we want to look at the probability that of over 80% that the hazard ratio is greater than 1. And for this, and I won't go into it, we used a 2-point prior, which was basically a prior that assumed there was a 50% chance that there would be no effect, hazard ratio of 1, and a 50% chance that there would be an effect of 1.5, okay? And we want to see what the probability was that what's the pointer? The probability was that the hazard ratio was greater than 1. And we determined the threshold for advancing to phase 3 of 80%, and in fact, it failed to meet it. It failed to meet it. So the effect, the virological effect, was significant, but it was not massive, basically. And I won't go into this. So this study also allows us to do additional verification. So we're interested in pharmacokinetics, and we're interested in virological characterization, and you saw a poster about that last night. So in pharmacokinetics, molnupiravir is a very unstable metabolite. It had to be rushed on ice, and spun down within 10 minutes. So there was a situation where one Saturday I came in, there was a patient. We have a red team with red runners and a green team with green runners and a lab team. There were 16 people for one patient coming in who failed screening. Okay, so this is how intense it is over weekends. But you get good data. So these are the plasma across the 3 doses that we studied, okay, 300, 600, and 800. And these were salivary concentrations. And this was nasal mucosal concentrations of drugs, so very interesting when we talk about mucin later on. The last one is drug to tears. So we're interested in the drugs penetrating into these matrices as a proxy for potentially preventing transmission as well. And we're interested in accumulation, and you see the same thing over. So you can see that penetration of molnupiravir into saliva was 3%, but it's 20% in nose and tears. Okay, so that's important information to have too. And then this poster, many of you will see last night, and I'm very grateful to Aya and Julian for looking at this, and they will laugh at my trying to explain this, I'm sure. But in purple is molnupiravir day 1, 3, and 5. Green is controls, and you can see that molnupiravir does what it says on the tin. Molnupiravir, of course, has this ambiguity for binding to G or A, so you're more likely to get transitions compared to transversions, and indeed that is the case. That is the case over the period of study. And for deep sequencing, again, Aya had this on her poster. This is day 1, day 3, day 5. As the study progresses, we've got nasopharyngeal swab samples in patients on placebo and on molnupiravir. Green indicates the most common amino acid, so it's 100%, and each dot is a patient, and blue indicates everything else. And as you can see, as you progress through the days of treatment and viral recovery, you see virus is becoming more heterogeneous as it within the host, and arguably more in molnupiravir than placebo. But actually, there's this viral evolution on the host, which is not entirely surprising given what we've heard this morning. So conclusions, we've got some, we like to think this is statistically efficient. We've produced data in a vaccinated cohort with contemporaneous viruses. I won't go into that, but there's a preprint out. And to make the point that actually clinical efficacy is something separate. It's very host dependent. You know, people who are hospitalized and die have risk factors, and that's not present in these models. There are other studies that are going on. So we've looked at molnupiravir, we're looking at high-dose nitazoxanide. We've completed the phase 1, and that's rolled over from the UK to phase 2 in South Africa. We have completed phase 1, a first-in-human study of VIR-7832, which is a sotrovimab analog with FC mutations that push the half-life out to about 6 months, which is the LS mutation, and then an XX2 mutation that gives the antibody a vaccinal effect. So it's actually immunostimulatory as well. Okay, so that's an interesting one. Phase 1 completed. Phase 2 terminated because of potential futility, and that's because of the whole story about sotrovimab and Omicron. You do need target engagement for the vaccinal effects. We have another one, which is in phase 1, which is the first in COVID evaluation of intravenous favipiravir. So the favipiravir trials have been disappointing, but all at a dose that's been far too low, 800 BD, not supported by animal studies. So animal studies suggest you need to go much, much higher. So we've got, and that's a huge pill burden with that, so we've gone into intravenous favipiravir, and we're opening in the next couple of weeks a combination of Paxlovid and molnupiravir, and there'll be other studies in development as well. Now, so that was just a very quick view of the Agile study. There are, of course, many things coming. There are antibody and antibody-like molecules, nanobodies, DARPins, things like that. There are TMPRSS2 inhibitors, incredibly disappointing so far, at least for treatment. RDRP inhibition, mutagens, and of course the big excitement, which is the protease inhibitors, particularly MPRO inhibitors. But they're not the only ones. Of course, there are things that will target maturation and release and other areas. And actually, last night's posters I thought were very encouraging, looking at the potential number of potential targets that are there. So currently, we've got this situation where we have treatments that are effectively small molecules, remdesivir, molnupiravir, or nirmatrelvir, and one monoclonal bebtelovimab. And the situation with sotrovimab is a little bit unclear at the moment. But we have a situation where the target population that we're giving to is now different. Okay, so people who are dying today of COVID are not the same people that are dying in 2020 of COVID. Okay, so they're very different. And I'll come back to that in a minute. And people dying in high-income countries and the people dying in low-income countries are also different. So I'm a great believer that actually you need to build that into your early phase trials. So you need to build in multimorbidity, polypharmacy, people with renal failure, liver impairment, people with loads of drug interactions, which is a big problem with Paxlovid. So we also created this drug interaction website to support treatment with antivirals, and that's been an important part of our drug discovery work. And currently, it informs guidelines across the world. There's about 1 million searches are downloaded every month across 220 countries, and it supports NIH guidelines and European guidelines. And you can see the number of drug interactions that you can have across cancer and cardiovascular, antimicrobials, immunosuppressants, particularly tacrolimus, solid organ transplants. And this leads me to my closing observations, really, which is the target population is different. In high-income countries, these are cancer, hematological oncology, particularly solid organ transplants or bone marrow transplants, people in chemotherapy, people suppressed. And there is a use also for antivirals to keep the NHS open, to keep hospitals open, and to keep health services going. Okay. Now, in low-income countries, that's different, okay? That's HIV, unvaccinated, a huge... And how representative are our trials for that? So I was talking to one of my colleagues in South Africa. He says in South Africa, most of the immunity comes from natural infections, not vaccinations. In Uganda, I was just saying just now, Omicron is known as God's vaccine because it works and it's free, okay? And then pregnancy, breastfeeding, there are other situations that are different. And one of the problems is that the informativeness of modern trials. So we're now, as death and hospitalizations goes down, and some of you will see the panoramic preprint, 0.8% in the UK. Then trials are going to get bigger and bigger and bigger and bigger and bigger. And so there's a temptation to use virology, which I think is not a great surrogate for clinical efficacy, or to use soft endpoints like number of days in hospital, number of visits to A&E, GP utilization, problems and things like that. And these are not informative for low-income countries that have to deal with malaria and HIV and diarrhea and respiratory infections. And lastly, I will say this. So this was something that I decided to do a weekend on call a few weeks ago when I looked in clinical trials gov at molnupiravir, Paxlovid, and remdesivir. And I looked at the countries where the registrational trials were done, okay, by Merck, by Pfizer, and also investigator-initiated studies, okay? And these were the countries that it was done. Then I looked at the countries that they were available in post-licensing, and that's what that looks like, okay? So there are limitations to this. This data is not easy to get hold of, and there are big procurements from Global Fund and ACTA and UNICEF, and we don't know which countries they're going to. But you can see, nevertheless, that there are countries that contributed to clinical trials that have zero access to antivirals, okay? And I think that's really, really... Are you upset by that? I think that's a scandal. Right, so these data come with caveats. They're not current and they're hard to get, but I think that we should challenge manufacturers when we do these publicly funded platform trials to say, actually, what are you doing about global access? I'm going to stop here and really tell you conventional drug development is going to change, I think. That's going to change. And I just want to make one point, because there's a conflation between what is affordable and what is effective. And I hear people saying, let's do repurposed drugs because they're cheap. Okay, I think what you do is get the best drugs and make them cheap, okay? I think that's what you need to do, and it's always about access, and I'll stop there. Thank you very much for listening.
Thanks so much. Saye, that was a lovely talk. Any questions from the audience? So, there we go. Rich first, maybe?
It's obviously a really agile platform, but you haven't talked about ethics, which seems to be very non-agile. Think about how you coordinate this with ethics.
So I'll just repeat, you can repeat that.
Okay, so the question was how to make ethics and the regulatory process agile as well as a trial platform. In the UK, we were lucky because the MHRA and the RECs gave us fast-track access.
The cost of all this. I was thinking outside of the pandemic, one of the limiting factors of the drug production is the sheer cost of it if the government's not picking up the tab. Does your shortening the time scale, does it actually save much money, or is it more intense?
I think it saves money through time, because the costs are so much to do with salary as well. And numbers of clinical trial participants. So if you concertina the whole process, then the salaries go down. So the costs are they're not cheap, but I think they are more affordable. And I think that you can count costs so many ways. I mean, the sooner you get an antiviral into a population, the more money you'll save overall society.
Any more? I wonder if I can just take the last question then. So with all the sort of experience they've garnered over the last 2 years, do you think there's anywhere else you can shave time off in terms of a clinical trial, with the next pandemic around the corner?
So, yes. So there's I didn't talk about peacetime work. There's a lot to do in peacetime. So sotrovimab was an antibody that was discovered in SARS-1. And then when that was over, they just put it in the freezer. I don't think we should ever do that with SARS-2. And then there's a lot of peacetime work. So in peacetime, you don't know what the next virus is. So you can optimize not the dose, but the dose range. You can do that. And so when the next virus comes along, you can tune the dosing to that virus. So there's a lot of work you can do in pharmacology and drug development in peacetime. Yeah.
Okay, thanks very much. And now we've got Dr. Saye Khoo from Pirbright Institute, who's going to talk to us about infectious bronchitis virus.
Okay, so I'm going to talk to you today about a recombinant IBV virus that exhibits a temperature-sensitive replication phenotype and one which protects against homologous challenge. So IBV is gamma coronavirus that causes infectious bronchitis. Infectious bronchitis is a respiratory disease of chickens. Infected birds don't gain weight as quickly, and infected layers lay less eggs, and those that they do lay are of poorer quality, so you get soft shells. So it's of huge economic importance. We do vaccinate. They're typically live attenuated vaccines. To generate these vaccines, you take a virulent field isolate, you passage it in embryonated hen's eggs, typically 80 to 100 times. So this takes a while. The molecular mechanism is unknown, so these vaccines present a risk of reversion. So there is a drive to develop ways to rationally attenuate. So that brings me on to actually the first project I ever worked on as a lab assistant, and that was generating a reverse genetic system on a pathogenic strain of IBV, which is called M41. So this was done in the early to mid-2000s when coronavirus reverse genetics was painful. There's only one way to describe it. It took years. And we finally made a recombinant IBV that we called M41R. So when we characterised this recombinant in the lab, it looked the same as M41CK, so we were fairly optimistic. However, when we put this virus into birds, so we had two isolates, 6 and 12, so they're in green and purple. When we compare it to the pathogenic control group, the birds aren't snicking, so that's a chicken version of a sneeze, and there's no tracheal rails, so that's like a rattle in the throat. So our recombinant wasn't causing any clinical disease. And IBV pathogenicity is determined on tracheal ciliary activity. So at defined points post-infection, you whip out the trachea from randomly selected birds and you section it. You take 3 sections from the top, 4 from the middle, and 3 from the bottom, and you assess the ciliary activity. So they're little cells that beat. So our pathogenic control is 0 at days 4, 6, and 7, and our recombinant was upwards of 75%, and was the same as our apathogenic control group and the mock. It was a surprise. So there was a lot of soul searching. Had I put the virus in the birds? Had I got the titer right? We did a lot of sequence analysis with other M41 isolates, and what we did is we found 4-point mutations in 10, 14, 15, and 16. We went about repairing those point mutations to generate a virus called M41K. This virus is pathogenic, but I'm not showing you the data. We also had lots of different combinations. And what we did was we identified that it was these two that were associated with an attenuated phenotype. So that's pro-85-leucine in NSP10 and Val393 in NSP14. So one of the other things actually I did for my PhD was looking at temperature sensitivity, and I decided just to throw in M41R because I thought it could be interesting. And we can see actually that M41R exhibits a temperature-sensitive replication phenotype at 41 degrees. So the core body temperature of a chicken is 41. So the respiratory tract will be higher, but obviously the lower respiratory tract as you get into the lungs is going to be at 41. So it doesn't replicate very well. Okay. So we did a lot of different combinations in those growth curves, and we identified that it was 10 and 14 that also caused a temperature-sensitive replication phenotype. So the big question was whether M41R would protect against challenge. So we did a vaccine challenge study. So we vaccinated 8-day-old birds. We either mock vaccinated or vaccinated with M41R. And then 3 weeks later, we challenged them, either mock challenged or M41CK challenged. And I'm only showing you the post-challenge data. So again, you look at snicking and rails. So our vaccinated group is in green. So actually, you can see that the birds aren't snicking. There's no tracheal rails. And IBV vaccines are, the effectiveness of them is measured differently to COVID vaccines. It's all done on tracheal ciliary activity. They're the European regulations. So for a virus, for a vaccine to deem as work, out of those 10 rings, 50% activity must be retained in nine of them. And when we look at our ciliary activity, so our unvaccinated pathogenic challenged group is at 0, and our vaccinated group is higher at 100%. And actually every bird in these groups at days 4 and 6 met this standard. The American standards for how they deem vaccines work is different to the Europeans. They look at challenge virus recovery. So we also looked at whether we could detect any challenge virus in various tissues, and also whether we could detect any RNA, and we couldn't detect any of that. So it would suggest that M41R is inducing a sterilising immunity response. However, the huge caveat is that our first sampling day is day 4. So it could be that the immunity induced just allowed for earlier clearance of the challenge virus. So in summary, mutations in NSP10 and 14 result in an attenuated phenotype as well as a temperature-sensitive replication phenotype. You need both the mutations in 10 and 14 for attenuation, but I haven't shown you the data. 14 will do most of the work for the temperature sensitivity. So the proline at residue 85 at NSP10, as well as the valine at residue 393, are conserved amongst the coronavirus group. So it is possible that these two mutations offer a mechanism to rationally attenuate not only other IBV strains, but other coronaviruses. Temperature sensitivity for an avenue for rational attenuation for vaccine development isn't unusual. It's done with flu. It hasn't been done with coronaviruses. It's possibly worth investigating. And our M41R protects against challenge, and that's in terms of ciliary activity, clinical signs, and challenge virus. And we published all of this data this year as part of 2 publications. So this one was out in January, and this one was just before the summer. So if anyone is interested, they can read up. And that's just to say thank you to the funders and the huge number of people that have worked on this project.
Okay, thanks, Sarah, for a lovely talk. We've got a question back there.
Sorry, this might be a late question, but have you looked at the chance of reversion?
Yes, so we...
Sorry, I'll just repeat that.
Okay, so the question of reversion. So we have passaged M41 in eggs, ex vivo tracheal organ cultures, and in cells 10 times, and we haven't seen any reversion at all. And that's, we did the cells at both 37 and 41. The industry standard for reversion from your seed stock is 6 passages, so it meets the requirements.
Any more questions? Sharon?
So have you thought about doing challenges with field isolates? Because I guess the problem with IBV is that the effectiveness of vaccines in the field can be variable, so
Yes.
you need to check it against.
So the problem, not problems with the work, but the things we need to explore is obviously this is done in SPF birds, and it's like a closed population. So we need to check it works in what I call dirty birds, but real birds. I know, it's terrible phrasing. And M41 is a real IBV strain. It's globally distributed. But for those that don't know, there's two types of IBV strains. You get classical respiratory strains, and you also get nephropathogenic. So these are ones that go into the kidneys. And we're currently doing it in a nephropathogenic strain, D388, if that means anything to anyone. That study starts next week, actually.
Just time for one more question, sorry, maybe.
Just one of the mutations you identified, did they arise during recovery of the virus or in the brain?
No, we made the exact sequence that we wanted to. What we found is that these mutations exist as a minority population in a virulent M41, and what we think happened, so our in-house sequence was generated in the late 90s. What we think is someone passaged their M41 too many times in cells, and then that population became dominant. That virus was never tested in birds, and we just ran with it. So, yeah, it was a happy accident.
Okay, great. I think it's time to move on to the next session now, but just thank the two speakers for some great talks in this one. Thank you.